Okay, once again, good morning, Ma. So in today's session, we are going to see the conversion of right linear grammar to, that is regular grammar to finite automata, as well as from finite automata to regular grammar. In the previous class itself, we have seen one conversion, but for your understanding, let me again put another example. So as we have discussed on that day, the what is a regular grammar? Can anyone say? Can anyone give the definition for regular grammar? Yes. Sharon, can you give the answer? It's Sharon is there. Roshan. So if you don't respond, I assume that you are not there. You are not present.
Yes, ma'am.
Yes, give me the answer. What is a regular grammar? Yes, do you know the answer or not?
No, ma'am.
Why? Have you taken notes in the previous class? Danush, those who are not responding,
Yes, ma'am.
yes, give me the answer for regular grammar. What is the regular grammar? See, if you simply sit beside in front of the mobile or your laptop and without taking notes for TOC class, it's absolutely a waste of time. Okay, simply because you have joined the meeting will not help you in learning TOC. You should take notes whatever I'm teaching and follow the steps properly and practice and get thorough in the concepts. So regular grammar is any grammar that is either right linear or left linear. We call it as a regular grammar. It will be either right linear or left linear. And what is right linear grammar? All the productions in the grammar will have at most one variable on the right hand side and that too on the rightmost side. Okay, like this. Okay, or it will have only the variable terminals, one or zero or more number of terminals. And in left linear grammar, the variable will be at the leftmost on the right hand side. Okay, okay, so this is the regular grammar. I hope you remember. So please take notes while I'm teaching. That will help you to study better. So this is a regular grammar, and this regular grammar, it represents the regular language. Okay, it represents the regular language, and for regular language, it can be represented. Already, we have seen that any regular language can be represented either using a deterministic finite automata or a non-deterministic finite automata or a regular expression. Okay, and all these are all equivalent to each other. From NFA you will be able to convert it into a DFA, and from finite automata you will be able to convert it into a regular expression. From regular expression you can convert to a NFA. Okay, so these are all equivalent and you will be able to do the conversions between them. And now, what the conversions, what we are going to see is that the regular grammar also represent the regular language. So will be able to convert a regular grammar to finite automata. Okay, a regular grammar can be converted into a finite automata. So since we have regular grammars in two forms, one in right linear grammar and another is left linear grammar. Okay, so RLG represents right linear grammar, and LLG represents left linear grammar. So from both the forms, it is possible to convert it into a finite automata. So you'll be able to convert right linear grammar to finite automata and vice versa. Okay. So from finite automata, you'll be able to convert it into a right linear grammar. And similarly, left linear grammar can be converted into a finite automata, and from finite automata, you can convert it into a left linear grammar. So actually, this is the conversion that we have seen on the previous class from right linear grammar to finite automata. But still, I'll give one more example for this also, and then we will see how from finite automata also you can convert that to a grammar. Okay. So first, let us do the conversion from right linear grammar to finite automata. Okay, that day we have discussed one example. So today we will move for another example. Okay, for right linear grammar to finite automata. Okay, so let us take this grammar. B naught gives A B1 and B1 gives AB B naught or B. Okay, so this is the grammar given. You can see that on the right hand side of the production we have at most one variable. Okay, we have only one variable, and here there is no variable, so at most one variable, 0 or one variable, and that variable it is present at the right end of the production. So now to convert this, this procedure already we have discussed in the previous class. I hope you remember. If you have not listened the previous class, kindly listen now. So now here the variables are, so what is the grammar given? Grammar will be of the form V, comma, T, comma, S, comma, P, right? So VTSP is the form of a grammar. So what is the variables given here? The variables are V0 and V1. Okay, they are the variables. And what are the terminals given? Terminals we have A and B. Okay, and here we have the start variable is V0, and these are the productions. Okay, these are the productions given for this grammar. So now we want when you want to convert a grammar into a finite automata. In a finite automata, what is that you need? You need to have the states, right? So a finite automata is, so this is given. Okay, this is the given part, and you want to find a finite automata. When you say finite automata, whether it is a DFA or an NFA, it is having the things like the set of states, the transition, initial state, and the final state, right? So now what is the how we are going? Which one we are going to consider as the state? Okay, when we are converting from a grammar to a finite automata, what are all the states for this finite automata? So the states are going to be the what are all the variables that are present in your grammar, that is going to be the states in your finite automata. Okay, so we have the states something like V0 and V1. Okay, so states are going to be V0 and V1, and the input symbols are the terminals present in the grammar. Okay, so A and B are the terminals that are present in the grammar, and that is going to be the input symbols for this machine or the finite automata. And then we have to write, and here the initial status V0 and the final status according to this. So we will have to take into final state VF. We want to have final state. And the transition functions. So how will you write the transition function? The transition functions, we can write it from the given grammar productions. Okay, so how will you write what it says from V naught? It goes to V naught gives A V1. Okay, that is on reading input A, it goes to state V1. So the transitions can be written as, sorry, here we want to draw the finite automata. So from we will be able to draw the finite automata. How we can do that? The states, the variables of that as the states. Okay, variables as the states. Let me draw it on the side so that you'll be able to follow it here. So this is the given grammar productions. Okay. So now we will draw the finite automata here. So V naught is one of the stage, and that is the initial state. Okay, V naught is the initial state. And what is the production given? For every production? We need to add an edge in the given in the finite automata. Okay, so from V naught on reading A, it goes to state V1. Okay, so all the variables that are used in the grammar is going to be the state here. Okay, and determinants are going to be input symbols in the finite automata. So V naught on input on reading input A, it goes to state V1. And again another production we have, that is V1 gives AB V1. So each and every production we are going to convert it into the finite automata. Okay. So from V1 on reading A and B, it goes to V0. So we are going to have an intermediate state also. Okay. Let us call that state as V2. Okay. So from V1 on reading A, it goes to V2. And from that on reading B, it goes from V1 on reading A, it goes to an intermediate state V2, and from V2 on reading B, then goes to V0. Okay, so from V1 on reading input A and B, it goes to V1. Okay? And then we have another production V1 gives B. So that means whenever there is only a set of terminals, it has to connect with the final stage. Okay, because that is the thing that is going to be useful for stopping your derivation. So from B, it goes to the final stage. Okay, so let us name the final stage as B. So this is the finite automata that we can draw from the linear grammar. From drawing from a linear grammar to a finite automata is very simple. Each and every production you need to convert it into a state connected with the edges. Okay, so the variables that are present in the production is to be converted into states. Okay, so this terminal we are going to convert it into the input symbol in the finite automata. So from V0 on input A, it goes to V1, and then from V1 on input A and B. Okay, so after reading A and B, it goes to V0. So while, as we know that we will be able to read only one input at a time. So when we read A, it goes to an intermediate state, say V2. From there again, when it reads B, it goes to V0. So on the whole, from V1 on reading A and B, it goes to V0. Okay, and when there are only terminals without any variables in a production, then this has to be connected with the final state. Okay, so now this is the resultant finite automata which is converted from a right linear grammar. So this is the first conversion from right linear grammar to finite automata. Now the next one we'll see from finite automata to right linear grammar. Okay, so we'll take the result that we have got here as the input. Okay, so what we want to do now, we want to convert from finite automata to right linear grammar. So from finite automata to right linear grammar. So what, let us take the input output that we have got from the previous problem as the input here. So what is the finite automata? V naught initial state on A, it goes to V1, and then on B it goes to final state, and here on A it goes to V2. Okay, this is the input. That is, given input is a finite automata. Now this has to be converted into a right linear grammar. So to do that, so then what has to be done? This finite automata has to be converted into the productions. Okay, when you say grammar, it has to be converted into the uh, right linear grammar productions. Okay, so how will we do that is that, so from the finite automata given, what we'll be able to assume is that the transition functions. Okay, because given is a finite automata. In a finite automata, we will have the transition functions, right? So the transition functions can be written from the given finite automata. So how will you write? Let me write it here so that it will be visible to you. So delta of what are the transitions available here from state V naught? Okay, on reading A, it goes to V1. Okay, so this is a transition function that can be taken from the given finite automata. How can we write the transition from state V naught? Okay, on reading inputs to state V1. Okay, transition of V comma A is equal to V1, and then from V1. Okay, from V1, so there is only one outgoing edge from V0. Okay, so that transition is over. Then coming to V1. From V1, we have two transitions, one on input A and another on input B. Okay, so delta of V1 comma A is equal to V2, and delta of V1 comma B is equal to VF. Okay, I hope you understand. From V1 on reading input A, it goes to V2, and transition of V1 comma B is equal to VF. Then coming to state V2. So from V2, we have one outgoing edge, that is, it is reading input B. So V2 comma B is equal to V0. Okay, and finally we have one more state, that is VF, and we don't have any outgoing edges from state VF. Okay, so there is no transition here given in the finite automata. So now what we have to do is, these transition functions, it can be easily translated into a right linear grammar. Okay, these transition functions can be easily translated into a right linear grammar. Simply by looking at the thing, we'll be writing it in the form of a production. Okay, so how you have to write? So take this variable from V0 is the left hand side variable in the grammar production. It gives A V1. Okay, V0 gives A V1. I hope you can look into the previous problem where we have been given the production V0 give A V1. Okay, so this is what is converted into this finite automata. Now from this finite automata, again we are converting back to the right linear grammar. So this production can be written as V0 gives A V1, and then V1 gives A V2. Okay, this transition function can be written as from V1 it gives A V2, and then V1 gives B VF. Okay, and then V2 gives B V0. Okay, now along with this, we also need to add one more production, that is from the final state. Whenever there is a grammar, definitely it should have some terminating point. Okay, it should have some production with only terminals, so that terminals or a lambda production, so that it will be able to stop the derivation whenever you are trying to derive the sentences. So here we can see that all the other productions are having variables. So every time when you apply these variables in a derivation, it keeps on it keeps recursively coming, but it will never end. Okay, so we need to have a stopping point, so that we can done using the final state, that is vf gives lambda. Okay, so this production is very important. You should not forget this particular production to be added in this grammar. Okay, all the other productions we can convert it from the given transition function. Okay, how we are writing the transition function? From the given finite automata, so that finally for the final state you include a lambda transition. Okay, so a lambda production, so this will give you the final set of right linear grammar. Okay, so do you understand these two conversions? Before moving on to the left linear grammar conversions, I want to know whether you understand this. Kindly respond in the chat box. Do you understand both these conversions? So I'm not sure whether you are all in the class listening or not. I didn't get even a single response. Did you understand these two conversions?
Yes, ma'am.
Yes, ma'am.
Yes, yes. Thank you, ma. One or two are responding in the chat box. Others may also respond. Okay, thank you, students. Thank you. Please do listen and take notes. So let me rub all these things. Now we'll go for the conversion from the left linear grammar, because left linear grammar is also a regular grammar. So as we say that a regular grammar can be converted into finite automata, we should also be able to do the conversion from left linear grammar. So the next conversion, left linear grammar to finite automata. So for this, let us take one more. Let us take a grammar. Yes gives capital A B or small a b. A gives A B or B B, and B gives B A or A. Okay, so this is the given left linear grammar. So now this left linear grammar needs to be converted into finite automata. I think this side. And then we also need to convert the given finite automata to left linear grammar. So please remember that for when we consider left linear grammar for these conversions, three steps we need to remember for both the conversions. Okay. So what are the three steps that we are going to follow is that first one is reverse, and then second one is construct, and the third one is again reverse. Okay, so let us see what this reverse construct and reverse in both the things. So both the conversions. So now first let us see how to do the left linear grammar to finite automata conversion. So what is the first step? It is given as reverse. Okay. So what is given here? We have been given a set of productions. Okay. So to convert it into the finite automata, the first step is reverse the productions, because what is given is the set of productions. Okay. The first step is reverse the productions. So how it what is the meaning of reversing the production? How we have to reverse it? We just need to, on the right hand side of the production, we just need to reverse whatever is present in the production. Okay, on the right hand side. So yes gives, so instead of AB we need to write it as BA. Okay, just reversing what is given in the right hand side of the production. Okay, so this is one production, and the next production is given as AB. Okay, so AB is reversed as BA. Okay, and then the next production we have A gives capital A small b. So this when get reversed it will give you BA, and then BB. Okay, capital B small b is reversed to small b capital B, and then BA can be reversed as AB, and small a, you can write it as it is. So the first step is you need to reverse the productions. And the next one is, what is the next step? It says construct. What to construct? We want to convert this given left linear grammar to finite automata. So we want to construct the finite automata. Okay. So that is the step 2. Construct the finite automata. So as we reverse the productions in the first step, can you observe anything here? Can you observe what kind of grammar after reversing we get? Can anyone try to say the answer? Initially, we had a left linear grammar, and in the, yes, very good, Solomon. It is a right linear grammar now, right? So as we reverse the productions, what we are getting is a right linear grammar. The right end we have all the variables, right? So now we want to, so now already we have seen how to convert a right linear grammar into a finite automata, right? So all these variables will be considered as the states, and based on this production we will be having the edges connecting to other states. So we can now easily convert this right linear grammar into a finite automata. So how will you do that? So the S is the initial state, and from S on reading B it goes to state A. Okay, so this production we are taking the first production, S gives BA. So how this can be converted into a finite automata? S and A are the states, and the connecting edge will be reading the input symbol B. Okay, then we go for the next production. What is the next production? S gives BA. Okay, so since it is having all terminals, it has to be connected to a final stage. Okay, so from yes already we have read B and it has been moved to state A, and from here we can read A. Okay, and it can be moved to a final state. Let us name it as capital F. Okay, so we have a final state. So yes, from yes on reading B and A it goes to a final state. Whenever there are set of only terminals, then it has to be connected with the final state. Then we'll move on to the next production, that is A gives BA. So A, from A on reading B, it again goes to A. Okay, so that means it is a self loop. Okay, from state A on reading B, it again goes to A, so it is a self loop. Then what we have, A gives B, capital B. Okay, so from A on reading input B, it goes to state capital B. Okay, so from A On reading B, it goes to capital B. So this production is over. Next, coming to the next production, B gives AB. So it is a self loop. So from B on reading A, it again goes to capital B. And then we have another production, B gives A. So since there is only one terminal, it has to be connected to a final state. Okay, so now this is the finite automata we have constructed from the grammar that is reversed in the first step. That is, it is actually a right linear grammar. Now, what is the third step? It is again reverse. Okay, so what we are going to reverse it now? What we are having at present now? A finite automata. So we are going to reverse this. Reverse the finite automata. What is the meaning of reversing the finite automata? What we are going to do is we are going to convert the initial state into a final. Initial state will be changed as final state, and final state will be made as initial state, and all the edges, okay, the direction will be reversed. Okay, direction of the edges reversed. Okay, so this is the meaning of reversing the finite automata. So how can we do that now? Now the state will become the final state. Okay, initial state will become the final state. So final state is represented using double circle. Okay, and this becomes the final state, and all the edges will be reversed. Okay, so that means when you take this edge, this will be reversed in this way, and we have the intermediate state A, and when you reverse this self loop, it will be as it is, it will be same. Okay, there is no change, and when you convert this edge, it will be like this, the reverse side, and now the state will be considered as the initial stage. Okay, so that means the initial state is represented using the arrow mark before that. So this becomes the initial state. And then we have one more, we have other edges here from A to B. So now this will be this direction. Okay, so instead of edge from A to B, we have to make it as B to A with the same input symbol. And from instead of B to F, it has to be F to B. Okay, and then we have also another self loop here. So that can be drawn as it is. Okay, so now this is the finite automata. This is the finite automata that we have for the left linear grammar. Okay, so this is the final output or the finite automata that is converted from a left linear grammar. Okay, do you understand this, ma? So these three steps has to be followed when we are converting it from a left linear grammar to finite automata, because we have already known the procedure for right linear grammar to finite automata. What we are doing is the left linear grammar is converted or reversed into the productions are reversed to make it as a right linear grammar. From there, we are constructing the finite automata. And since we want to convert the left linear grammar to finite automata, this finite automata is simply reversed. Okay, the initial state is considered as final state, final is considered as initial state, and all the edges or the directions were reversed. Okay, so finally we want to convert the finite automata to left linear grammar. Okay, we want to do the conversion from finite automata to left linear grammar. Again, these three steps we are going to use it here. So let us take one example. Okay, so let us take this particular finite automata. Now this has to be converted into a left linear grammar. So again, the first step to convert this is we want to reverse it. What do we have to reverse? The given finite automata. Okay, reverse the finite automata. So how we have to reverse the finite automata? Everything we will be, the final state will be converted into initial state, and the initial will be converted into final state, and all the edges has to be reversed. Okay, so while you are doing so, Q naught becomes the final state. And in this particular case, since all the edges are connected as a loop between two states, when you reverse this edge, it will be like this one. Okay, when you reverse this edge, it will be the direction will be reversed here, and again when this is reversed, this will be moved to Q1. Okay, so in this case, when you reverse both the edges, again it will be looking as a loop only in all the in all the cases, in all the edges. Okay, so what will you get? Again the same thing. Okay, because this edge will be now reversed to this one, and this edge will be reversed to this one. Okay, so now what is Q3? Since Q3 is the final state in the previous thing, now here Q3 is the initial state. Okay, so all the other edges are going to remain the same. Actually, it is reversed, but it is not. There is no difference because in all these states, the edges are acting as a loop between the states. So there is no, it seems that there is no difference. So this is the first step. We have reversed the finite automata. And what is the next step? You need to construct the grammar. Okay, construct the left linear grammar productions. Okay, we want to construct the left linear grammar productions. So how will you do the, sorry, we have to construct here. From the given finite automata, we are going to construct the right linear grammar. Okay, so from the right linear grammar, in the next step, we will again reverse this grammar to get the left linear grammar. So because from finite automata, we know how to build the right linear grammar productions. So how will you do that? The transitions, okay, the transitions available in these in this finite automata will be translated into a production. So we'll, since this is the initial state, since Q3 is the initial state, we will start from there. So how will you write from Q3? We have two outgoing edges. One is carrying input symbol 1 and another is having input symbol 0. Okay, so Q3 gives 1 where it is going Q2. Okay, Q3 gives 1 Q2 and another production is 0 Q1. Okay, 0 Q1. And then let us take the next state Q2. Q2 also it is having two outgoing edges. One is going to, on reading 1 it goes to Q3 and another on reading 0 it goes to Q0. Okay, so 1 Q3 or 0 Q0. Okay, from Q to 0 Q0. Then considering Q1. So from Q1 again there are two outgoing edges. 1 goes to Q0 and 0 goes to Q3. Okay, so 1 Q0 and 0 Q2. Sorry. 0 goes to Q3 and 1 goes to Q0. Okay, and then finally Q0. Q0 gives on 1 it goes to Q1, and on 0 it goes to Q naught. From Q naught on 0, it goes to Q2. Okay, so let me rub this for your understanding. So now apart from this, what other transition you need to add here? For any final state, there should be a stopping point when you are doing the derivation, right? So here the from this automata, Q naught is the final state. So Q naught gives lambda. Okay, so this transition for this grammar production also has to be included from the given finite automata. So now what is the step 3? What is the next step? We have to reverse the productions. Okay. So in the previous step, we have constructed the right linear grammar productions. So from this, we need to reverse it to get the left linear grammar. So how will you do that? The reverse is very easy from Q3. So this one Q2 can be written as Q21. Now in this case, which are all the variables actually? Can anyone say? In this grammar production, which are all the variables and which are all the terminals? Input symbols. See here, this right hand, left hand side things, these are all the variables, okay? Because what represent your variable? The state names, okay? So here, though it is represented as a lowercase letter, actually these are the variables because these are the state names, okay? So Q0, Q1, Q2, Q3 are the variables. So now when you are reversing the production, Q3 gives, so this Q1, Q2 has to be written as Q2, 1, and similarly Q1, 0, and then Q2 gives Q3, 1. I'm just reversing it, okay? I'm not doing anything else. Just from the given above productions, I'm just reversing it, okay? Q2 gives Q3, 1, and Q0, 0. Then from Q1, Q0, 1, or Q3, 0. And then from Q0, Q1, 1, or Q2, 0, or lambda. Okay, so now you can see that this is the final left linear grammar. Okay, so all the productions are having the variable at the left end in the right hand side of the production, or it will have a lambda. Okay, so these are the 4 conversions that we can do to convert from a regular grammar to finite automata, and then from finite automata to regular grammar. Is there any doubt? Do you understand this procedure? Yes or no? Only one? Okay, thank you, students. So all of you, please listen the class. So now let me take the attendance. Unmute your mic and quickly give me the attendance. Felix,
Ma'am.
Preetham,
Present, ma'am.
Shinai Babru,
Present, ma'am.
Jeffrey Jebastin,
Present, ma'am.
Ujjal, Ujjal, Nancy,
Present, ma'am.
Steve Abraham,
Present, ma'am.
Aditya,
Present, ma'am.
Soumya,
Present, ma'am.
Joseph Rajan,
Present, ma'am.
Jeffin Thomas,
Present, ma'am.
Ashish Kumar, Ashish Kumar, Varghese Shibu Samuel,
Present, ma'am.
Eric Izan, Eric Izan,
Yes,
Christina,
ma'am.
okay. Christina Sherin,
Present, ma'am.
Kayuri,
Yes, ma'am.
Sriram Prasad,
Yes,
Sriram
ma'am.
Prasad, Justin Sean,
Present, ma'am.
Jemima,
Present, ma'am.
Harsha Anna Daniel,
Yes, ma'am.
Jeffrey Roshan,
Yes, ma'am.
Naga Bhavani, Naga Bhavani. Yes, present. Christina Rajesh,
Present, ma'am.
Selvam Abhisha,
Yes, ma'am.
Rajesh Shekhar,
Present, ma'am.
Grace Angela,
Present, ma'am.
Mark Daniel,
Ma'am.
Santosh, Santosh,
Present, ma'am.
Giovin,
Present, ma'am.
Darwin, Darwin, John Jnana Kanmalai, 1168 John Jnana Kanmalai, Abhishek,
Yes, ma'am.
Maunika,
Yes, ma'am.
Dunamis Blesson,
Present, ma'am.
Srinivasa Reddy,
Yes, ma'am.
Abhishek Abraham,
Yes, ma'am.
Panduranga Prabhu,
Yes, ma'am.
Hari Gokul,
Present, ma'am.
Prasanna Kumar,
Present, ma'am.
Jerlin Lijo,
Present, ma'am. Journal ledger.
Pavani,
Yes, ma'am.
Swapna,
Present, ma'am.
Arun Kumar,
Yes, ma'am.
Sasidhar Reddy,
Present, ma'am.
Johnson,
Yes, ma'am.
Austin,
Present, ma'am.
Kambam Sanjay,
Present, ma'am.
Monish Sai, Monish Sai, Peter Rajkumar, Peter Rajkumar, Sri Sai Rahul Reddy,
Yes,
Ma'am,
ma'am.
ma'am, Monish present, ma'am.
Monish present, Sai Rahul,
Yes, ma'am.
Sugin Joshua,
Present, ma'am.
Sugin or Sujin?
Sujin, ma'am.
Sujin, okay. Anjani,
Present, ma'am.
Kavin,
Present, ma'am.
Johnson,
Yes, ma'am.
Revant Julian, Revant, Vishwant,
Yes, ma'am.
Solomon Raj, okay, present. Sharon,
Present, ma'am.
Sai Srujan,
Present, ma'am.
Srikant Nayak, Srikant, Vishwamohan, 2005, Vishwamohan, Roshan,
Yes, ma'am.
Tirumalai Nambi, Tirumalai Nambi, Mithuna, okay, present. Hamsavardhan,
Present, ma'am.
British Anand,
Present, ma'am.
Asban Gibson,
Present, ma'am.
Darla,
Present, ma'am.
Dhanush,
Present, ma'am.
Sibi,
Present, ma'am.
Hariharan,
Present, ma'am.
Okay, the absentees, I'll put it in the chat.
Ma'am, Ujjal present, ma'am. Ma'am, URK 19 CS 100 present. Ma'am, actually, I was attending my dose since no one was at home, so that's why.
Ma'am, 2005 is present, ma'am.
And
Yeah, my mic
5, I
was
have
not
called you several
my
times.
ma'am, yeah, my mic was not proper. Okay, from next time be fine. Yes, ma'am. Ma'am, your mic is lagging. Ma'am, can you repeat it?
Have you listened to the class?
Yes, ma'am. Yes, ma'am. I have.
Okay.